Okay, so Unit 1, Day 4b. Yesterday we composed functions. Today we're going to decompose functions. So it kind of sounds gross, but in this case it just means to take them back apart. So compose means put together, and then decompose, we're going to break it back down. So in calculus, sometimes this is important. When you're doing certain kinds of processes, you got to be able to identify that it is a composition, and B, what was the parent function and such. So this will help us definitely setting you up for next year. So begin by looking for what's the hidden parent function, and then we've done a whole list of parent functions. The squares, the radicals, the reciprocal function, all those we did a couple days ago. And now we want to try to identify them, and then break them back apart. And we're going to try to look at this, and we've got the h is over here, so that's the function that is the answer of the composition. And we're going to try to figure out what's the g that's inside of the f. So the f would be like the parent function, and the g went inside of it. So let's try to figure out what is f of x first. What's the parent function, the big guy, the big picture thing? So like in this case, the big picture function is that there's something being squared here. And the thing that's inside of a squared would be the g of x. It's the hidden function that got composed into it, and that would be 2x plus 1. Okay, now as I start doing these, I'm going to go kind of fast. If you want to test yourself, just pause it, and then play and see if you're right, and then pause again, and you guys know how to do that. So this guy here, yes, there's a squared. So you might think it's an x squared, but it's not that something's inside of an x squared, it's that something is inside of a cube root. So the parent function here is a cube root function, and the thing that got plugged inside of a cube root was x squared minus 4. Okay? And I do want to mention along the way that there are oftentimes more than one right answer. So it's not that my answer is the only one. You may say, well, why wasn't it this? And it's possible for it to be a different answer. There's different compositions that when you compose them, you get the same resulting composition function. This guy here, what's the big picture function is there's a 1 over x. Okay, it's a reciprocal function. What's inside of it? An x plus 2. Okay. This one here, a little tricky, maybe a little bit tricky here to see, but if you notice, the thing that is being repeated is right here. There's a negative x squared in the top and the bottom. Okay, so that means we plug something here and here, so the original function must have been x plus 3 and 4 minus x. I'm sorry, actually, this one, it's actually a plus, because if I got a negative and a negative, that means this is a negative x squared, so that needs to be a plus in there. So x plus 3 and 4 plus x, when we plug negative in, that's what made it a minus x squared in the beginning there. The next one, I guess I should have numbered these. I want to say like number 5, but it doesn't have a number. So the next one, the big picture, something being squared. The thing inside, x plus 5. Okay, here, yes, there is a squared involved, but the big picture, the function that the squared's inside of, is a cube root, and then 5x squared plus 1 is on the inside. This guy here, there's a cosine x that's inside of the exponent, so it's a 2 to the x function, and then the function inside is cosine x. And then the last one here, the last guy, what's going on? Well, it looks like that I see it twice right here. That function must be, so this is a square root of x squared plus 1, is inside of a x minus 1, x plus 1 function. You see, like with these two guys here, these weren't typical parent functions that we're used to seeing, but it's the basic function that it all started with, and then these went inside of it. So we say parent function. These aren't like by definition parent functions, but the rest of those were. Let's flip this guy over then, or go to the back side. And it says the number of bacteria in a refrigerated food, or bacteria in refrigerated food is given by this function. So this is saying that the number of bacteria depends on the temperature. And then down here, it says the temperature depends on the time. maybe we turn the, or maybe this one, the compressor was running and then it stopped, and from that time on the temperature starts to go up. Like the compressor runs, it gets cold, and then the temperature starts to rise slowly, and then the refrigerator comes back on, it goes back and forth. So maybe it started right here and it ended there, so this is time 0 and this is times 3. So the temperature is increasing as time goes on. Let's see, for the first hours, this is hours, so the first 3 hours. So notice the domain is from 0 to 3. So it's only true for the first 3 hours. So the temperature depends on the time, the bacteria depends on the temperature. So you kind of see that in the end, the number of bacteria actually depends on the time. Not just the temperature, but also the time. So I could use a composition here to speed things up. Instead of plugging a time in here and then getting the answer and plugging that in up here, I can compose them and make one function. So that's why I want to compose. So the number of bacteria, and I want to compose that with T of little t. Okay, and this would be N of, and T of little t is 4t plus 2. Now plug that in for every t you see up here. So this was 20 times something squared minus 80 times something plus 500. And I'm supposed to plug in 4t plus 2 into every spot there. Okay, so first off, I'm going to square this guy and then distribute the negative 80. So that'd be let's see, minus 320t minus 160 plus the 500 on the end. I do some distributing here. So this, distribute everything out, all this. Now look for like terms. So again, now this, part of the interpretation then, this is N of little t now, because little t went to big T. Well, now that's t. Plug that in, simplify it. So this is the number of bacteria with respect to time, and this is going to be 320t squared. Let's see, combine the t's, those are actually gone, and then combine these three together, and this would be a positive 420. So this is the number, the interpretant's meaning, this is the number of bacteria with respect or depending on the time. Depending on time, as long as the first 3 hours. Now, and like I said, we're just trying to speed things up. The temperature depends on time. The bacteria depends on temperature. Well, that just means that the bacteria depends on time, so we did that quickly. So if I just want to find out how much bacteria is, depending on what time it is, I can skip the temperature altogether. I don't have to find the temperature. I just got this function right here. It does both of them all in one. Now find the time when the bacteria, so that means N of something is going to equal 2,000. So when does the number of bacteria equal 2,000? So I'm going to plug that in. Actually, I should say T for time. Plug that in right here. I'm going to find a time. So I'm going to have 2,000 equals 320t squared plus 420. And now it's just simple solving. So subtract 420 from both sides. 1580 equals 320t squared divided by 320. So the time squared, and if we just reduce this, you get 79 over 16. Square root both sides, I got square root of 79 over 4 plus or minus. Off the page. Now this one I got plus minus. Now could I have a negative time? Not when I'm talking about this. So real life problem. So it's a positive radical 79 over 4. I want to make sure that's between 0 and 3. So if that's not between 0 and 3, if this number is not between there, that means it never happens. It never reaches 2,000, at least not for the information I've been given. So when I put that in the calculator, then I'll just put it this way. I'll put a squiggly line, which means about. So this is about 2.22 hours, which is between 0 and 3, so that means it is accurate. If you want to get real fancy, that's 2 hours, 13 minutes, and 19.2 seconds if you want to be down to the exact time that it happens. So yeah, so there's the time, which this is probably good enough too.